Welcome to this explainer. We're diving straight into one of the absolute greatest marvels of human engineering, the electrical grid. It's a massive continent-spanning machine that has to flawlessly balance raw physical power with delicate dynamic stability every single second of the day. But today, that machine is fundamentally changing. We are actively replacing heavy spinning metal with static solar panels and wind turbines. So, how do we keep this newly digitized grid from collapsing? Let's find out.
Here's our roadmap for today. We'll start with the power supply chain, move into substation safety and fault currents, then tackle the renewable energy shift, the looming threat of low inertia, and finally, how we're stabilizing the modern grid.
Part 1. The power supply chain. Let's trace how electricity actually gets to your outlet.
To really grasp the future of the grid, we have to ground ourselves in how it works right now. The supply chain basically has three legs: generation, transmission, and distribution. Power surges out from massive plants across high-voltage lines. We're talking up to 765 kilovolts here. These lines use aluminum for conductivity and steel for shear strength. From there, step-down transformers at substations drop the voltage for local distribution. But here's the kicker. Thanks to distributed energy resources, or DERs, like your neighbor's rooftop solar, it's not a one-way street anymore. We've now got power flowing backwards from end users right back onto the grid.
Now, here's a fun little fact. We call it a grid, but it's really not a neat, perfect grid pattern at all. It's actually this incredibly complex web of redundant paths. Why? Economics and reliability. Engineers route power through the absolute cheapest paths available while making sure that if one line snaps, the power just instantly detours. The lights stay on. Moving on to Section 2, Substation Grounding and Safety, managing some seriously massive physical forces.
Let's zoom in on the physical hardware for a second. Substations step down those insane high voltages, and honestly, the human stakes here are huge. According to IEEE standards, one of the biggest hazards during a fault is something called step voltage. Imagine you're standing in a substation during a massive electrical surge. Step voltage is the difference in surface electrical potential between your 2 feet if they're just 1 meter apart. If you take a step without a properly designed grounding system, that voltage difference could literally be fatal. That's exactly why these substations are built over massive, complex grids of buried bare copper to equalize that surface potential and keep everyone safe.
So, it makes you wonder, right? How on earth do engineers calculate for the absolute worst-case scenario? How do they mathematically prepare for a direct lightning strike or a massive short circuit to ensure all that buried copper is actually going to be enough?
That brings us to Section 3, Understanding Fault Currents, the literal mathematics of disaster.
Take a look at this IEEE formula. This is how we calculate the maximum magnitude of a zero-sequence fault current. Don't worry, we aren't going to memorize the variables today. But the big takeaway here is what this math represents. It calculates the absolute ceiling, the maximum electrical current that will dump into the earth if the system fails. The result of this equation tells grid designers exactly how much copper and how many grounding mats they need to bury in the dirt to safely divide and dissipate that catastrophic energy before it melts equipment or hurts someone. But, physics is rarely perfectly neat. Fault currents aren't smooth alternating waves. They have an initial DC offset, which we calculate using a decrement factor. This offset essentially makes the current asymmetrical. So instead of a smooth, rhythmic push, the grid takes a sudden, violent shove. This pushes temperatures way higher, and incredibly, it exerts mechanical forces almost 4 times greater than a perfectly symmetrical current. The physical abuse the hardware has to endure is just immense.
So how do we actually survive all that? Well, it takes a coordinated physical defense. First, line entrance surge arresters catch the immediate lightning strikes. Second, that buried grounding grid divides the fault current. And third, redundant circuit breakers slam open to isolate the interrupted power. Now, you'll notice substations are usually built with bus bars in multiples of 3. Why 3 phases and not 1? Because the entire global grid runs on 3-phase power. If you've ever seen a motor on single-phase power, its torque pulses twice every cycle, literally shaking the shaft. But on 3-phase, you get smooth, constant torque with 0 pulsing. Those 3 sinusoidal waves are offset perfectly by 120 electrical degrees, meaning the pulsations cancel out. And the massive structural advantage for grid designers, because that power delivery is constant, you can push the exact same amount of power using significantly less copper than a single-phase system. Plus, if any single path fails, redundant backups ensure the whole shebang stays alive.
All right, Section 4, the renewable energy shift. We're in the middle of a massive systemic transition.
We are actively rewiring the planet right now. Globally, solar PV is hitting around 35%, and wind power is at 30% in terms of renewable grid penetration. And look, this rapid deployment is absolutely fantastic for reducing carbon emissions and fighting climate change. But from a purely operational standpoint, it is throwing a massive curveball at grid managers. Our traditional power systems were built around giant, heavy, rotating synchronous generators. And renewables, they play by completely different physical rules.
Which leads to Section 5, the threat of low inertia. What happens when we lose our physical shock absorbers? This shift introduces a totally new engineering threat to grid stability. Let's compare the old guard with the new. Traditional synchronous generators, think of those massive steam turbines in a nuclear or coal plant, have incredible heavy rotating mass. That gives them natural mechanical inertia. Plus, they naturally output high fault currents, which makes triggering safety relays super easy. But renewables like solar panels, they are what we call inverter-based resources. They connect to the grid through power electronic converters. They have absolutely zero inherent physical mass spinning around, meaning zero physical inertia, and they produce a vastly reduced fault current.
So why does that matter? Because system inertia is essentially the shock absorber for the entire grid. It's the ability of the power system to naturally resist sudden, dangerous changes in frequency, simply by leaning on the stored kinetic energy of those giant, spinning metal masses. When you swap out a spinning steel turbine for a static, silent solar panel, that vital shock absorber just vanishes.
And the consequences of losing that shock absorber are pretty stark. When you look at highly renewable grids, low system inertia now causes a massive 35% of all stability challenges. Right behind that is generation variability at 25%, because, the wind doesn't always blow and the sun doesn't always shine. And then we have voltage instability at 20%, which tends to crop up in weak grid conditions where short-circuit capacity is vastly reduced.
We can actually see the math behind this crisis in something called the swing equation. That df/dt you see on the left is the rate of change of frequency, or Rokoff. The h in the denominator, that is the system's inertia. It's simple division. As h gets smaller, meaning we add more static renewables and retire more spinning turbines, that rate of change speeds up dramatically. So if there's a disturbance, the frequency drops incredibly fast. Grid operators and control systems suddenly have a lot less time to react before a total system blackout cascades across the network.
Finally, Section 6, stabilizing the modern grid, how we're fighting back with cutting-edge tech.
To solve this low inertia problem, engineers are opening up a pretty wild technological toolbox. First, we're swapping out older, passive grid-following inverters for new grid-forming inverters that actively establish voltage and frequency on their own. Second, we're pairing those with incredibly fast-responding lithium-ion energy storage systems. Third, we're deploying virtual inertia control. And fourth, when we really need to brute force it, we install synchronous condensers. These are literally massive machines that just spin without a mechanical load, purely to inject real, physical inertia back into the power network.
But what's really mind-blowing here is that concept of virtual inertia. We are literally programming advanced software control strategies to make a completely static, silent piece of electronics, like a solar inverter, adjust its power output instantly to mimic the exact physical behavior of a heavy spinning metal generator. We are basically tricking the grid into thinking the heavy metal is still there, artificially slowing down those dangerous frequency changes to keep the whole system stable.
Which leaves us with a pretty profound question to chew on. As we aggressively decarbonize and pull out the physical, spinning heart of our traditional power plants, can advanced software, giant batteries, and smart electronics truly emulate the heavy, reliable physics of the past? Navigating this transition from heavy metal to dynamic digital control is, without a doubt, the greatest engineering challenge of our generation. I hope this explainer shed some light on exactly what's at stake. Thanks for joining me, and keep questioning how our world works.